current correlations in the fractional quantum Hall effect.
Thanks. So it's a pointer. Let's see. Okay. And this is pointer. All right. So good morning to everybody. It is a pleasure for me to visit for the first time in my life this beautiful country and this beautiful center. So I'd like to start my presentation by thanking the organizers for inviting me here today. So today I'll be talking about chirality and current correlation in fractional quantum Hall systems, which is part of a project I'm still working on in collaboration with Gabriele Campagnano, who right now is at Naples University in Italy. So to briefly outline what I'll be talking about, I'll first of all spend a few words by reviewing some basic facts about the nature of charged excitations on top of a fractional quantum Hall system, on top of a fractional quantum Hall ground state. In particular, I'll focus onto the peculiar nature of the charge and of the statistics of those charged excitations, namely the fact that they are expected to carry both fractional charge, that is a charge that is a fraction of the electron charge, and fractional statistics, that is a statistics that is a fraction of the fermionic statistics. After reviewing, briefly reviewing the standard theoretical approach to those fractional charge excitations emerging at the edges of a fractional quantum Hall bar, I'll discuss about tools for experimentally probing the fractional charge, which has already been seen, that I'd say about 20 years ago, and how to possibly probe the fractional statistics, which has never been clearly detected experimentally so far. At this point, I'll discuss about our original contribution to the subject, that is about our proposal for detecting the fractional statistics in a simple say beam splitter-like experiment realized with quantum Hall edge states. Eventually, I'll be summarizing our results and I'll discuss about possible further perspectives of our work. Now, I think the simplest way for presenting fractional quantum Hall effect is by reviewing some well-known diagrams. I'm sorry about the very low quality of the plot. Anyway, what is plotted here is the Hall resistance and the longitudinal resistance, say ohmic resistance, measured by means of a 4-probe arrangement in a fractional quantum Hall bar, that is a 2-dimensional electron gas, which can be realized, for instance, at the interface between semiconductors in a silicon MOSFET or at a gallium arsenide heterostructure as a function of the applied magnetic field, which is orthogonal to the 2DEG, so to 2-dimensional electron gas. As you can see, there's large windows of variation of the applied magnetic field, even several Teslas, in which the ohmic resistance keeps to 0, while the Hall resistance is quantized in some plateaus. The values that the Hall resistance takes on a plateau are very interesting, and actually it is more interesting to look at the reciprocal of the Hall resistance, that is at the Hall conductance, which on a plateau is a multiple of the universal quantum Hall conductance E squared over h. So it is E squared over h times this number nu, which is dimensionless, and is either an integer, in which case one speaks of integer quantum Hall effect, or a fractional number. Typically, P and Q are integer numbers priming with each other. Q is odd. And in the following, I'll be mostly focusing on the so-called Laughlin's fillings, that is the ones with Q being an odd number and P equals to 1. Now, by means of very simple arguments, it has been argued that under minimal assumptions, the elementary excitations, the elementary charged excitation, which is realized on top of the ground state of the system on one of these Laughlin's fillings, should carry both fractional charge and fractional statistics. Let me briefly outline how the assumptions work. Now, the minimal assumption, actually, I think I should go to, no, let me come back to this slide. The minimal assumption is that the system's ground state is non-degenerate and it must be fully gapped. Now, having assumed this, let us consider a two-dimensional electron gas realized in a very peculiar form, that is a disk with a hole in between. Let us imagine to switch on very slowly, adiabatically, a magnetic field through the hole realized in the center of the disk. Now, if all the process is very slowly, so that the gap never closes, we can imagine to increase the magnetic flux from, say, 0 to the universal quantum of flux phi 0. After doing so, we end up with some Hamiltonian H phi 0, which is well known to be gauge equivalent to the original Hamiltonian in 0 magnetic flux. This means that H phi 0 and H 0 are isospectral. So whatever we have done adiabatically to the original ground state of the system, eventually we have taken it to some excited state of the Hamiltonian in a 0 applied flux. Now, what should this excited state look like? Let's come back to the disk. Let's use a very simple classical electrodynamics argument to infer what the new state should look like. We are applying a magnetic flux through the hole, slowly increasing in time. By means of Faraday's law, this gives rise to an electric field which is, say, orthogonal to the radii. This electric field takes this form, and since we are at the hole plateau, so the ohmic conductance is 0, there's only off-diagonal hole conductance, the induced electric field will give rise to a net flow of charge from, say, one boundary, one edge of the disk to the other. So the net charge moving between the two edges at the time t will simply given by this formula, which means that if after a long enough time phi of t has become equal to phi 0, the net charge that we will have transferred from one edge to the other will be just, so delta phi equals phi 0 means that delta q is just the electron charge times the number nu. Now, nu is 1 over m at the Laughlin's filling. So what we have really done to the state of the system is to create two localized excitations of opposite charges lying at the edges of the system, so well separated in real space, each one carrying a charge whose absolute value is nu times e. So it looks like by means of very simple arguments, one is expected to recover excitations with a fractional charge. Of course, one has to prove that one has at least to give insights in favor of the ground state of the system being non-degenerate and fully gapped. And actually, Laughlin was able to do so by explicitly constructing a trial wave function for the fractional quantum Hall ground state. This is a many-body wave function for electrons in 2 dimensions. Zi is simply xi plus I yi, so the complex coordinate giving the position of the ith electron in the system. That is again a collective wave function. It is a trial wave function which is known to have, was proven to have an excellent overlap, slightly less than 1, with the true ground state of the system. It describes a disordered liquid ground state which is non-degenerate, and it is fully gapped in the bulk. Not only that, by means of a slight modification of this wave function, it's also possible to construct a trial wave function describing a localized charge depletion around point Z0, whose net charge is just what is expected for the elementary charged excitation. So it's E star equals nu times E. That is interesting because this Z0 here, though in the following I'll be mostly calling it the coordinate of the fractional charge quasi-particle, or what is it usually referred to of the Laughlin's anyon at Z0, it is not actually a real coordinate. It is a sort of label of a collective wave function. We should actually think of the excitation as like a bump of charge, which is centered at Z0 and spreads over a distance which is of the order of the magnetic length, which is a small number because B is huge, but is still finite. So this is for one charged quasi-particle at Z0. It can be generalized to describe two quasi-particles. Again, remember the argument I provided you before. ZA and ZB are labels of a collective wave functions, which if we neglect the small finite extension of the quasi-particles, can be thought of as the coordinates of the centers of the two quasi-particles. So this is the wave function, just to speak, for two Laughlin's quasi-particles localized at ZA and ZB. If we regard ZA and ZB as coordinates for the particles, we can let then ZA adiabatically make a round trip in time around ZB, and then eventually compute the total Berry phase accumulated at the wave function, at the many body wave function, after we have come back to the starting point. This Berry phase comes out to be 2 pi over nu, and it is known to be twice as large as the phase associated to the swapping of the two identical quasi-particles with each other, which basically means that together with the prediction of excitations with fractional charge, we also got, by means of the same token, a prediction about particles carrying fractional statistics as well. The statistical phase is 1/2 of this number, so it's pi times nu. You see that when nu equals 1, so when we have back particles with the charges of electrons and holes, the statistical phase is pi, as it is appropriate for fermions. When u is 1 over m, it's a fraction, again, of the fermionic statistics. So this is basically what I mean when I speak about fractional statistics. Right. Now, just a few couple of slides about theory. As I hope I have been able to show you before, these charged excitations are expected to show up as free propagating charges at the boundaries of a finite size system. Now, if we want to theoretically describe them, we have to switch to a field theoretical framework to describe excitations in a one-dimensional system. So in the Lagrangian formalism, this is going to be a 1 + 1 dimensional Lagrangian. This is actually at nu equals 1, so this describes fermions. This Lagrangian is for a couple of chiral fermions with opposite chirality. You should actually think that fermions with localized at either edge have got a well-defined chirality just because they are moving at the edges of a system pierced by a huge magnetic field, which basically forces, for instance, fermions moving at the topmost edge here to move from right to left, fermion moving at the bottom edge to move from the left to right, assuming that the field is coming out of the board. Right. So without doing anything else, this Lagrangian describes actually a very boring system. So very few things can be measured here, just because anything interesting associated to transport is basically associated to backscattering events, which cannot take place if the system is just the one described by this Lagrangian, just because there's no room for backscattering, for, say, intra-edge backscattering. So to induce some backscattering events, so some interesting features in the transport properties of the system, one has to let the two edges to talk to each other, which can be done in a real-life system by pinching the whole bar with gates, so to induce a non-zero tunneling amplitude for fermions from, say, minus edge to plus edge and vice versa, with the corresponding tunneling Lagrangian taking this form. So starting from this framework, one can then compute average values of the density and of the current operators for chiral fermions, then use them to study transport properties and so on. Yes, please. Pardon? Yeah, next slide. Next slide. So if nu is not 1, first of all, we are describing some system whose excitations have very little to do with particles and holes, so something which is not a firm liquid anymore, just because strong electronic correlations here have broken Fermi liquids picture. Actually, a fractional quantum Hall system is one of the very few well-known examples of non-Fermi liquid states. Another one was the two-channel overscreened Cond effect, studied by Ian first. So the same should happen at the edges. So the edges are not expected to be described by a sort of simplified Fermi liquid picture anymore. They are 1 plus 1 dimensional correlated electronic systems, in which case one has to give up the Fermi liquid picture and resort to a Lauthinger liquid picture in which the elementary field is a bosonic field. Here we have actually a pair of chiral bosonic fields describing collective plus-1 modes at the two edges. In this framework, so if we use this as a free Lagrangian for two chiral Lauthinger liquids, this is the corresponding, say, bosonized version of the density and of the current, of the charge density and of the charge current operators. And operators describing creation and annihilation of quasi-particles with fractional charge are realized as no linear functionals, so vertex operators, of the bosonic fields phi plus minus. So this is the, say, new less than 1 version of the free Lagrangian, and this is the new less than 1 version of the tunneling Lagrangian. Actually, this should be more complicated than this because there should be some subleading terms which can definitely be neglected if one is interested in low energy, long wavelength properties of the system. So, this is the theoretical machinery one uses to study transport properties of the system in case in which nu is less than 1. And one can compute things by doing some standard maths within this framework. What kind of things? For instance, since we are letting the two edges talk to each other, we can compute the backscattered current, so the tunneling current between the two edges, and some higher order momenta of the current. Why should we do so? Well, first of all, let me say that the operator describing the backscattering current can be simply derived from the tunneling Hamiltonian, and it takes this form. Now, if we want to study transport properties of the system in their full glory, we should take into account that to have a non-zero current, we have to bias the two edges at a finite voltage V. For some reasons, which I hope will be clear in the following, we should also take into account finite temperature effects. And of course, in principle, the tunneling amplitude, gamma, between the two edges can be any number. So we should take all these three ingredients into account to cook up our recipe. So T, B, and gamma. To take all three of them into account gives rise to a sort of very complicated non-equilibrium problem, which one should address within the so-called non-equilibrium Keldysh approach. In fact, in the following, I'll discuss about a simplified version, which though we, simplified version of the problem, such that though we still use the Keldysh approach, in fact, in the regime I'll be considering, it is basically equivalent to the to a standard perturbative, time-dependent perturbation theory in gamma. So in the following, I'll be assuming that this pinching is very is sort of small, so that gamma is a sort of small number, and we can get reliable results by just stopping our calculations to leading order in gamma. And so one can do calculations to leading order in gamma these two quantities, that is the backscattering current and the momentum, second order momentum of the backscattering current can be readily computed. So this is the result for the backscattering current in the zero frequency limit. Just to define some symbol, tau c is some non-universal cutoff. Just let's leave it aside for a moment. Beta is 1 over kBt. I'm sorry, too many gammas. Anyway, this gamma with the brackets is just Euler's gamma function. And say weak backscattering means that we are doing stuff to leading order in the tunneling amplitude. So this is the current. This is the so-called noise, so the second order correlation function of the current. And that is interesting because you see that both currents and noise take a similar dependence on the cutoff and other non-universal quantities. Basically, sigma b is different from 0 for two good reasons. So this measures fluctuations in the current. Why the backscattering current should fluctuate? Well, because we are doing stuff at finite temperature, so just because of Johnson noise. But it should also fluctuate at zero temperature, for the very simple reason that we are shooting quantized charge against a quantum point contact. So once the charge hits the quantum point contact, it can decide whether to go straight or to come back. This is an intrinsically stochastic process which makes the noise, so the fluctuations, to be non-zero even when t goes to 0, but v is finite. In this regime, we recover the so-called shot noise, and if we look at the Fano factor, the regime in which t is very small, so the noise is mostly quantum, the striking result is that the Fano factor is just equal to E star, so to the elementary charge carried by the charge carrier. Now, starting from these theoretical predictions, there were, back to 1997, so more than 20 years ago, two beautiful experiments. Here I'm reporting the plot from the experiment done in at Weizmann's group. So this was done in Heiblum's group, but there was a similar experiment done at Saclay in Laughlin group. So what they were able to measure was basically the ratio between the current noise and the backscattered current in the, say, quantum regime. You can see that this is the prediction in the case in which the elementary charge carried at the edges is E, and this is what they measured. So it is actually E over 3 because the measure was done at nu equals 1/3. So far, fractional charge. In a sense, we are measuring nu by measuring E star. But coming back to this slide, you can see that this parameter nu, the so-called filling factor, has a twofold, say, nature. It is telling us what is the fractional charge, but it is also telling us what is the fractional statistics. What this experiment measures is, say, the fractional charge, so nu for what it contributes to the fractional charge. What about fractional statistics? We need a sort of independent measurement. I mean, in principle, these guys could be fermions. They actually shouldn't be bosons because they intrinsically obey in exclusion statistics. So how do we know that they obey fractional statistics? Well, we should find a way to swap their positions, for instance, in real space, or to make one of them go around the other, which basically in an experiment done with quasi-one-dimensional systems, such as the edge states of a fractional quantum Hall sample, means doing interferometry. So we are talking about solid-state interferometers. There was again a beautiful experiment done back in 2003 in Moti Heiblum's group, in which they did electron interferometry. So this is an electronic Mach-Zehnder interferometer they realized. They basically shooting, right, this is like a scheme of a cartoon of how it works. They are shooting in currents from, say, here, and, well, I cannot, yeah, they're shooting current from here, then they split the beam, and then eventually they recombine the beam and look at the interferometric pattern, and they were able to measure the interferometry contributions to the detected current at D1 and at D2, which is interesting because besides providing us with a proof of the electronic interferometry, this result also gives us information about how the collected currents depend on the applied magnetic flux. Phi is the ratio between, say, the Arnold-Bohm flux, phi 0 times 2 pi, and as expected, the current is a periodic function of phi, say of phi b, with period equals to phi 0. So this is very good, this is interesting, but this is done with fermions. How about doing the same with anyons? There was a number of theoretical proposals. Possibly the most remarkable one was again done by people related somehow to Weizmann, at least by Geffen. So there is a FIS review paper by Lowe, Feldman, and Geffen, in which they basically propose to redo Bloom's experiments, but now with fractional quantum Hall edge states. So they designed, that's a theory paper, an anionic Mach-Zehnder interferometer. There was also a modified version, so Amby Brown into his interferometer, to which my friend Gabriele contributed when he was at Weizmann. What is the result? So what should we actually look at in an anionic interferometer? Well, again, we might want to look at the periodicity of the current as a function of the applied magnetic flux phi. It comes out that because of Byers-Young theorem, despite the charge now is reduced to a star, still the periodicity doesn't increase. So the periodicity is still equal to phi 0 independently of nu. So there's no way of seeing anything because of the periodicity. But Lowe, Feldman, and Geffen were able to show, by means of very clever and beautiful calculations, that there is some evidence for the statistics in the dependence of the phi-dependent contribution to the total current on the amplitude gamma 1 and gamma 2 that are the scattering amplitudes associated to, right, these two quantum point contacts. It is clever, it is beautiful, it has so far never experimentally seen. It's quite challenging actually to experimentally detect the evidence for the statistics, which according to Lowe, Feldman, Geffen proposal should be contained in this exponent B appearing in the, say, formula for I phi gamma 1, gamma 2. So basically they predicted that this term should be proportional to the difference between the current when say both Q quantum point contacts having a finite backscattering amplitude minus the current when the second quantum point contact was, say, closed. So gamma 2 equals to 0. This exponent B is basically pi times nu. So that is interesting, but again it's sort of challenging. That's why Gabriele and I proposed a different possible way of detecting some evidence of the fractional statistics. Now, you can see that this cartoon looks quite simpler than the ones I showed you before about interferometry. This is just a beam splitter. One can make it with quantum particles, with bosons or with fermions. One can shoot particles from sources S1 and S2. They are splitted by the beams. They are scattered by the beam splitter. one can collect particles at D1 and D2 and eventually look at the stationary density-density correlations between the densities of collected particles at D1 and at D2. Now, under the assumption that one is shooting particles from thermal sources, so S1 and S2 are sort of thermal reservoirs for bosons and fermions, it is a well-known result that these correlations are equal to the squared modulus of the scattering amplitudes R, say from 1 to 1, times the square modulus of T from 1 to 2, times something which gives already informations about the statistics. So N1 and N2 are the thermal distribution functions for particles in S1 and S2. They can either be Bose or Fermi statistics according to whether we are dealing with bosons or fermions. This plus or minus sign overall just means that bosons exhibit bouncing and fermions anti-bouncing. So just discriminate between exclusion and non-exclusion statistics. So this is a quantity one can measure in a very simple experimental arrangement, which is expected to give us information about the statistics. So our wonder was, how shouldn't we try to repeat the same calculation with anyons, so with fractional charge quasi-particles, and see what we can get. That is actually what we did. And in doing so, we had to think of the analog of the beam splitter realized with fractional quantum Hall edge states. In fact, it is something I already showed you before. It's just a quantum point contact. So just to explain what is this cartoon about, these are reservoirs, so mu1, mu2, mu3, and mu4 are chemical potentials for thermal reservoirs, from which we should charge into quantum Hall edge states. So let's look, for instance, at what happens here at this edge. We are shooting in charges here. So we are shooting in quantum Hall quasi-particles moving through this edge. They go straight, then they meet the quantum point contact. They can either go back to the opposite edge, which is again chiral, so they will tend to propagate this way, or they can go straight. So in a sense, this gamma is the analog of this semi-reflecting mirror. So we have to locate D1 and D2, and the natural choice is that D1 corresponds to some point x1 after the quantum point contact on this first edge, and D2 corresponds to some point x2, again after the quantum point contact, in the direction in which quasi-particles move inside the edge. So eventually what we want to compute is the density-density correlations between measured quasi-particle densities, charge densities at x1 and x2. In fact, sorry, too fast. In fact, since, as I showed you before, we are dealing with chiral, one-dimensional systems, the current is basically proportional to the density operator. So that's the reason for the title. Current correlations basically means apart from, for an overall constant, density correlations in these systems. So we actually did the calculation. Again, this looks like a very challenging Keldysh-like calculation, but in fact we stopped to leading order in the tunneling amplitude between the two edges, gamma. So again, was a bit challenging, but not too much. So we did some standard Luttinger liquid calculations, and this is the result. Now, this red formula, you already saw it before. It's just the backscattered current, so the tunneling current between the two edges. Let me comment a bit about this additional formula. You see that in addition to the symbols I had before, here we had to introduce another function, psi, which is the d gamma function. There's a minus overall sign, which takes into account the anti-bouncing nature of Laughlin's anyons, so this sign is right. And what we can do now with these two quantities, for instance, we can look at the same quantities they looked at when carrying out the prediction about the Fano factor being equal to the fractional charge in the quantum limit. So let's consider the quantum limit in which E star V over KBT is much larger than 1. Let's look at this ratio, and this basically gives us the same result as the Fano factor above. So from current correlations, one can extract the charge of the elementary charge carrier. But now we might want to consider a different limit, what we called thermal limit. So the limit in which now the relevant scale is KBT. So KBT is much larger than E star V, though E star V is still to be finite to have a non-zero backscattering current, of course. We can work out the asymptotics of our formulas in this regime. So this is some straightforward expansion of Euler's gamma and D gamma functions. This is the result. We look again at ratio and we find this interesting result. Now, let me first of all focus on these square brackets. The square bracket, whatever is inside the square brackets, is a sort of textbook results. This is what you would get with electrons, except that now here we have E star. So in our view, this basically means that if we add nothing after the closing bracket, our system has got charge carriers whose charge is E star, which, except for that, behave just as electrons and holes in a Fermi liquid. So had we had nothing after the brackets, this would mean that we are dealing with charges, with particles, with fractional charge, but statistics that is the same as the statistics for electrons and holes. So fermions with fractional charge. In fact, it is not so. We have this additional factor gamma nu, which is 1 when u equals 1, as it is appropriate for particles and also for standard fermions. But when u is different from 1, this factor is a huge number. So it already, when u is equal to the simplest Laughlin's filling, which is 1/3, this number is higher than 6. Second non-trivial Laughlin's filling, 1/5, it's about 16. This factor, which is given by a simple formula in terms of the gamma function, is something that shouldn't be actually attributed to the charge. It is some additional effect which, in a sense, in our view, must take into account the whatever is in Laughlin's anyons that is not concerned with charge. So gamma nu is a sort, we conclude that gamma nu is a sort of evidence for the second nature of nu, that is for its effect on the statistics of charged quasi-particles. So being able to measure this ratio in the thermal regime and getting a result that is this times some number which is different on 1 should be a simple, straightforward to detect evidence in favor of particles having fractional statistics together with the fractional charge. Okay, this is more or less what I just said in words. So to conclude, I hope I've been able that while current noise has proven a while ago to be an excellent mean to recover the fractional charge of Laughlin's quasi-particles, there is a slightly different quantity that is current correlation functions, by looking at which one can both recover informations on the fractional charge as well as on the fractional statistics of Laughlin's anyons. That is our main conclusion. What we are doing now is to try to find some analogous tools to apply to no Laughlin fillings in which the nature of the edge excitations is a bit more articulated, a bit more complex than in Laughlin's filling. That is, for instance, when U equals to third, or in which the true nature of edge excitations is still controversial, that is 5/2. And that is more or less it. So I'd like to thank you for your attention, and let me stop here.
Questions? Do you hope to see any non-abelian statistics in these other quantum Hall states by measuring current correlations?
We are, the answer, if you say I hope, the answer is yes, though so far we've only been doing calculations for abelian statistics. So what I can tell you is that there should be a possible way of finding some evidence for, say, non-charged branches of excitations, which do not affect transport but should contribute to statistics, which should happen to at mu equals 2/3, for which the standard model predicts that one has two excitation branches, one charged, one neutral. So yeah, the answer is yes, though we're still not working on that. We're actually working on 2/3 right now. That will be possibly the next step after 2/3.
Any more questions? If not, let's thank Domenico again. Okay, so now we have a lunch break. We have one more talk in the afternoon and the poster session. And let me also take the opportunity to